Okay, I guess we should start since it is 10 after. Today's lecture is going to be a little bit shorter, mainly because it's mostly pictures, and there's not much I can talk about pictures. But they do say 1,000 words, they say. So this week we're going to finish up some applications of double integrals and then move to vector fields, which is really our first foray into actual vector calculus. So first, consider what we mean by the length of a curve. So if you wanted to do this experimentally, if I gave you a curve, you could take a rope and lay that rope over the curve and then stretch the rope out and measure it. Right? That basically is an analog to what we mean when we say the arc length. Now, the name of the game for integrals was just adding up a bunch of stuff. What is the bunch of stuff we're going to add this time? Well, if we can break the curve into incrementally smaller arcs, then we can add the length of these arcs to obtain what we call the arc length. Here's a picture. Here's a curve in the blue. And the length of that line, the pink line, is approximately equal to the length of the curve. Is it going to be less than? Is it going to be shorter or greater? The length of the line will be shorter. Well, is there any case where the length of the line can be longer than the curve that it's approximating? I don't think so, because any curvature is going to give you more. The best you can get is a line approximating a line where there's zero difference. What is the distance between pi and pi plus 1 here? Two arbitrary points on this curve. I wanted to hear something like the square root of the sum of squares. Right? That gives you the distance between any two things in a grid. So if this is an approximation to the length of this curve, this is a better approximation to the length of this curve, and we can continually segment the curve into arbitrary many pieces like this and add the lengths of the lines. Now what we want to do is make the length of these lines sort of infinitely small and do an integral instead. So the length L of the curve C is approximately the sum of the length of the line segments from the point pi to the point pi plus 1 over some interval. For n segments, this is given by, well, the sum of the distance between the first point and the second point and the third point and the fourth, all the way up to the n minus 1th point to the nth point, right? Where, again, the distance between 2 points is the square root of the sum of squares. Here I put it's typical to square the left-hand side of this equation so that we get rid of roots, but equivalent to what I'm saying. Okay, so here's some mathematical witchcraftery that we need in order to translate this sum into an integral. Do you remember what the mean value theorem states? Anyone give it to me in English? Really? Who taught you calculus? The mean value theorem says that if you have a curve and you pick 2 points on that curve and draw a line between those 2 points, that the slope of that line, right? Well, okay, let me say this again. If you take 2 points in a curve and draw a line between them, you should be able to find some point in between those 2 points such that the slope of the tangent is equivalent to it. So here I have drawn 2 points on this curve, and that other point with the dashed line is a point at which the tangent line has the same slope as the slope given by connecting those 2 points. And this is always possible provided that the curve that we're speaking of is continuous and doesn't loop over itself, for example. In any case, the mean value theorem assures there are some xi asterisks, some sample in between the ith point and the ith plus 1 point, so that the slope of this line, right, fx, like the fxi minus fxi minus 1 over xi minus xi minus 1, this is the rise over the run, there's going to be some point that we can choose that's going to have the same slope as this. So mean value theorem assures that there is xi asterisk in this range such that the slope of the line is equal to the derivative evaluated at that point. If I take this equation and I multiply through by the denominator here, we get f evaluated at xi minus f evaluated at xi minus 1. F is the function that gives the curve. Maybe I didn't make that very clear. But if we multiply through by here, we see that the difference in the height, sometimes what we would denote as delta yi, is equal to f prime of that sample times the change in x. Now, it's change of x here and not change of xi, because when we're segmenting the curve into pieces, we're assuming that we're just breaking the x-axis into equally sized chunks, right? So that delta x is going to be the same no matter which two x's we're comparing. The delta y's will be changing according to where we are on the curve, right? So this is why this is a delta yi and this is a delta x. So from this slide, just take that such an xi asterisk exists so that we can replace this relation with the one down here. From that last slide, we can derive this. The length of a curve divided into n segments is given by the sum of the distances between n points on that curve. By the definition of distance, we can swap out the distance from pi to pi minus 1 with the square root of the sum of the squares of the components giving those points. We can continue. From the last slide, we determined that the change in y's here is delta yi, and the difference between any two x's is going to always be the same. So we're going to swap that out for delta x. The last slide, we proved that delta yi can be replaced with xi asterisk times delta x applied at the derivative, where this xi is just any sample point between the ith point and the ith plus 1 point. From here, we can simplify. I took this delta x, so there's a delta x squared here, a delta x squared here. When we remove that delta x squared from the square root, it becomes a delta x without the square. So this is just a simplification of this, and thereby we have an integral, right? This is an integral by definition. This is sort of the moral that I've been trying to push on you guys, that this symbol here, this integral symbol, is a notation. It's just a notation for adding up an infinite number of stuff. This is no different type of math. It's really just a different symbol that changes this into this. Right? It was okay to think about integration giving you the area under the curve, but it's a very myopic way of looking at it because it has so much more utility than just calculating that. For example, calculating the length of the curve. Okay, so I have that the length of a curve divided into an infinite amount of pieces along the interval a through b is equal to the integral from a to b of the square root of 1 plus f prime x squared dx. And so now we can give a definition for the arc length. This is either a definition or a proposition, depending how you want to set it up. But we're the mathematicians. We get to set the rules, so let's say it's a definition. Our definition of the length of a curve is this. Right? It's the integral from a to b of the square root of 1 plus f prime squared of that curve. So here's a curve. Y squared is equal to x cubed. I'm giving 2 points on that curve, 1, 1, and 4, 8. What is the arc length of the pink distance along that blue curve? Well, this is easy. We just have to utilize the equation that we just made. Well, first of all, realize that there's a symmetry here about the x-axis. Right? There's a top half of this curve and a bottom half of this curve, which is just the reflection of it in the x-axis. So since we're being explicitly told to find the length between this point and this point, it would be ambiguous if I said, what is the length of this curve between x equals 1 and x equals 4? Because you wouldn't know if you're measuring the top half of the curve or the bottom half. So you really have to give 2 points on that curve, right? So for the top half of the curve, I can say we have a function y equals x to the 3/2, and we know that the derivative of y with respect to x gives us 3/2 x to the 1/2. And so the arc length formula says that the length of this curve from 1 to 4, right, x equals 1 to x equals 4, is equal to the integral from 1 to 4 of the square root of 1 plus f prime squared dx. So let's just take these values and plug them into here. This is the integral from 1 to 4 of the square root of 1 plus 9/4 x, right? That's 3/2 x to the half squared, gives you 9/4 x dx. And using calculus, this works out to 1/27 80 root 10 minus 13 root 13, right? I'll leave it to you guys to work out the details. I'm no longer going to do every step of these integrals, especially if they're univariate and simple. Surface area. This is another thing that we didn't cover, but we can use integrals to solve it. I was trying to think of a similar way of giving an analog for the surface area as I did the arc length, and I couldn't think of one. Maybe if you have like a fisherman's net, and you lay a fisherman's net over the surface, and then stretch out that net and measure it somehow, right, by counting up the sort of the squares of the net, that would be it. But that's very close to actually what the mathematical definition is. So I will simply say that the surface area of a solid object is a measure of the total area that surface of the object occupies. It's sort of a circular definition, but okay, surface area is the surface area, right? We can calculate this length. Well, first of all, realize that since we have an arc length, we can already do this, right? If you want the surface area of something, you can just add up an arc length and an arc length and an arc length and an arc length and an arc length, and if you're putting these lines beside each other, what you're actually constructing is a surface, right? So we could do an integral over the arc lengths, but let's just redevelop it all over again. But a lot of these questions you can already answer just by using the fact that you know an integral does an infinite sum. Okay, so here's a picture of what we're going to try to do. Here's a piece of a surface S, and there's a point Pij on that surface. And what we want to do is we want to estimate the area that the Pij gives, right? So we have some points, you have some delta x and delta y, and now we need to estimate the area given by that square. Well, we can calculate this direction and this direction, right? Those are the partial derivatives in each of those directions along x and y. And if we move delta x down this length, or this direction, and delta y down this direction, then how can we get the area of this? Well, it's the vector from here that stops here, the vector from here that stops here, and we take their cross product, and that gives us the area of that parallelogram. That's something that you should remember from linear algebra. It's also something that we talked about in double integrals when we were working with arbitrary domains, right? But the point is that if you take the partial derivatives in both directions, multiply them by how far along you want to move in those directions, and then take the cross product, that's going to give you the area of a portion of the tangent surface at the point Pij. So just absorb this picture. So now we have a surface, and we know how to find the area at a given point if you want to move a little bit in x and a little bit of y. So now we're just going to play the integral game and say, okay, take your surface, make it into a grid, choose a point, right, a sample point from each point in this grid, and then sum the areas of these sort of little tangent rectangles. So the area of the surface S is given by the limit of m and n both going to infinity. You want to divide the surface in x an infinite amount of times and in y an infinite amount of times. But we're just going to add up this Tij, which again was the cross product, or the area of that surface, and we want to do that in an infinite amount of time. So I'm going to show you how this expands so that we can recover the integral. Well, I've shown on that picture that the area given by Pij is given by the cross product of these two vectors. If I remove the length here, this is going to be the square root of the sum of squares. And I can remove delta x and delta y from this. And this is equal to the double integral over d of the square root of the sum of squares of the partial derivatives, plus 1. Right? So again, it's not really crucial to understand that. For those of you who want to look over it, look into Stewart's calculus textbook. They go into a lot more detail than I do. The conclusion or the point is that the surface area is given by this definition. Right? The area of surface S, and it has to be given by a function, and you have to have continuous partial derivatives, is given by this integral of the partial derivative of f with respect to x, f with respect to z, and who can guess why this 1 is here? We could follow the pattern here. If we swap out f for z, this would be dz dx squared, dz dy squared, and what would this be? dz by dz squared, right? dz by dz is 1, that's squared, so it just sort of illustrates that there's actually a pattern in this. And this pattern's fulfilled actually by the arc length equation as well. Here's this question. You're going to have one of these questions on your homework for sure, because I put it there. Find the surface area of the part of the surface z equals x squared plus 2y that lies above the triangular region T in the xy plane with these vertices. Okay, so you have some surface, you have some triangle in R2, and you want to know the surface area over that triangle. Well, first realize that the region T is easily given by 0, 1. We could draw this, but just use your imaginations. We need to go from 0 to 1 in x, and we go from 0 to x in y, right? If we were to draw this, you'd have the y equals x line moving out like this. Using the definition for the surface area, which is all you will have to do, we calculate the area as equal to the double integral over d, our region, of the sum of the squares of partial derivatives in every direction. If I swap out, our f is x squared plus 2y, so the partial derivative with respect to x is 2x. The partial derivative with respect to y is 2. And squaring each of those gives us 4x squared plus 5. That's 4 plus 1 down here. And eventually, you get 1/12, 27 minus 5 root 5. Right? So easy peasy. You just got to get into this form. One more before we move on to something a little bit more interesting. Find the area of the part of the paraboloid, right? So it's upper half, that lies under the plane, z equals 9. That is to say, that satisfies z is less than or equal to 9. So how do we do this? Well, first realize that the z equals 9 plane intersects the paraboloid in a circle. Right? So it's everything above this circle is the thing that we want the surface area of. Right? Therefore, our integrating region is going to be the disk of radius 4, centered at the origin, which are all the points x, y, such that x squared plus y squared is less than or equal to 9. Using the definition, which is, again, all you will have to do, just write it out. The area is given by the double integral over the region D of the square root of the sum of squares of the partial derivatives in every direction. Here, our equation is x squared plus y squared minus 9 equals z. So we have, did I do this right? Well, okay, so it's 1. I don't know why this is out of order. It's 1, then 2x, and then 2y. So how would you deal with this now, if your region is a disk? Yeah, maybe you caught a glimpse of that for too much. But I'm going to assume that you would have done it anyway, so good. That's very reassuring. Yeah, so you should, at this point, a light bulb should go on above your head. You say, oh, I'm integrating over a disk. A disk is a rectangular region in polar. I can integrate over a rectangular region, so let's switch everything. So it's as simple as going from this Cartesian representation to this polar representation, RD theta, and work it all out, and you'll get this is equal to pi 6, 37 root 37 minus 1. And I welcome you to double check this and prove me wrong. Okay. I think these are the right answers. Here are a couple interesting exercises for intrepid individuals. Do an arc length calculation to prove that the equation for the circumference of a circle of radius r is 2 pi r. Right? How did these sort of Greek geometers determine these equations for the shapes and for the areas and circumferences of certain platonic solids? Right? We developed the equation for the volume of a sphere last week, and it did require some non-trivial mathematics. We had to do a triple integral over a region in a different coordinate system. So why don't you give that a try? How would you do this? What's the first step of this question? Well, I just told you how to take the length of a curve. What curve gives the circle of radius r? That's the unit circle, so you're close. X squared plus y squared equals r squared. Gives you the circle of radius r, right? So you want to take the integral over that circle, right, from minus r to r, but really you'll be doing a polar calculation, right? If you switch it to polar, you'll do an integral, and you can work this out. Another interesting question is to prove that the surface area of a sphere is given by 4 pi r squared. I've given you both the equation for surface area and arc length, so you should be able to do these. When I was a student, I always found it interesting to go and work out these equations. Maybe that's why I had no friends. Okay, so here's the true topic for this evening. And again, I won't keep you nearly as long as I have other weeks because you can only go through this topic by looking at pictures. So there's not much explanation required. Though we will be doing some multiple choice questions together. I wish we had these clickers. Do you guys have these clickers here at U of N? There's some courses where they insist that you buy like a remote, so when you go to the lecture, they can say, do you think that the answer is A, B, C, or D? And the whole class votes. In stats, they use it. And they supply them. Oh. Stats has all the money. Anyways, it was an interesting way of trying to keep people interested. But I can feel that I've captured your attention so well that I don't need these clickers. But anyways, who can tell me what we're looking up here on the board? Oh yeah, drag, wind speed of an airplane. So you want to take an airplane, you want to make sure that it can fly. That is, it sort of utilizes the Bernoulli principle in the correct way. So you take a model of your airplane, you put it in a wind tunnel, and you fire wind at it. And you can study the eddies that come out at the end. If you want to study anything, the first step is to convert that anything into something that you can represent using mathematics. Right? If it can't be representable in mathematics, then you really have no hope in studying it. That's the purpose of mathematics. So a vector field is going to be what mathematically represents something like this, like a wind flow. But there are many other areas where you've already seen other vector fields in your daily life. Anyone can give me an example of a vector field that they would show on TV every day? You wake up in the morning and you want to know if it's going to rain or if it's going to be windy. Weather map. Surely you've seen pictures like this before. Where's the American? Certainly you've seen pictures of this. It's Katrina. Yeah, this was a really, really big hurricane that did a number on the Yanks. But you can see that these arrows are just telling you the direction of the windfall. You can sort of intuit that if I stuck you in here, you would be turned around in a circle and sort of sucked into the middle of this vortex, the eye of the storm. I think I have to. Can anyone from physics tell me one other area where vector fields are important? I'll give you a hint. It has to do with iron filings. Magnetic fields. Strong forces, right? Is magnetic a strong force or a weak force? No, it doesn't depend who you ask. There's a notion of strong forces and weak forces in physics. Is it a weak one? I think nuclear forces are the weak ones. In any case, I'm not a physics teacher, obviously, but for you physicists, these vector fields are going to be extremely important. Right? For people who want to model anything, these vector fields are going to be extremely important, which is why I went through a great deal of effort to draw things. Okay, so a vector field in 2D. All the examples, well, except maybe the first one, at least this and this, are examples of a vector field that is given in a plane, right, or what we call a 2D vector field. Two-dimensional vector field is given by a vector function, right? So you have to give me a function which takes something and returns a vector, right? Any function that does that is going to give you a vector field. We can visualize these vector fields, as we already have done, by drawing arrows to represent the vectors at the starting point x, y. So this is something that students always mess up, right? Remember that when we used to deal with vectors, that our assumption was that all vectors are centered at the origin, right? That if you had a vector here, or if you had a vector that was pointing in the same direction of the same length elsewhere, we considered those the same vectors, right? But these vector fields would be very useless if we drew all of the vectors at the origin. You'd have the origin and a million arrows coming out of it. So suppose I have a function, vector function f, which, given the point 4, 3, returns the vector minus 3, minus 1. This is how you draw it. So at the point 4, 3, draw the vector minus 3, minus 1. Right? Do not connect the point 4, 3 with the point minus 3, minus 1, which is the mistake everyone makes. You want to draw this vector, minus 3, minus 1, at 4, 3. And how do you do that? Well, here's 4, 3. This tells me to go down 1 and go left 3. So go down 1, go left 3. So what is this point here then? 1, 2. Made that one easy. I pointed to it. Right, so keeping that in mind, that you go to a point, get a vector, and then draw the vector at that point. If you can remember that and draw like that, then this should be easy peasy mostly. Right. We can't draw every arrow, obviously. There's an infinite amount of them. Right? How many arrows do you want to draw between 0 and 1 on the real scale? Well, it's up to us. Right? So here's an example. Here's a vector function xy, or here's a vector function f, which given xy returns the vector minus yx. So let's calculate some of these vectors at totally arbitrary points. Right? The amount of points we take and where we take them is up to us. Well, I guess the responsibility is on us to draw the vectors at enough intelligently chosen points so that we're actually indicating the behavior of the vector field. So let's calculate some of these vectors at these points. What is f evaluated at 1, 0? Well, 0, 1. I'm not going to go through each of these, but what is f evaluated at 2, minus 2? F evaluated at minus 2, 2 is 2 minus 2, right? Switch them and negate the first. Okay, so let's plot the results. So in particular, let's just remember that at the point 1, 0, I want to draw the vector 0, 1. So at 1, 0, that's 1 unit along the x-axis. Wait, which way are you guys looking? That's 1 unit along the x-axis. And from there, I want to draw a vector that is 1 unit pointing upward. Yes? Which one? Minus 2, 2 and minus 2, 2? Okay, clearly one of these is wrong. Because they both, so let's backwards engineer. So this is wrong? So if I want 2 minus 2 here, this was supposed to be minus 2, minus 2. Okay. I'll fix it, but probably not. I needed either someone to take down the errors or email them to me, but I am converting the slides into notes. Is that something that's worth my time, or? Okay. I can't. Well, it's just going to be the slides, but in a more compressed format with an index and stuff that I can do. Okay, so you guys will use it, right? Okay. It's coming. So here is the picture of the vector field at some of the points that we've chosen. So I said at 1, 0, we want to draw the vector 0, 1. Here you go. At 2, 2, I want to draw minus 2, 2. So, here's 2, 2. 1, 2, 1, 2. And I want to draw minus 2, 2. So from here, I move back 2 and up 2. That's how I do it. Right? At 0, 3, I need to move left 3 and up 0. That also helps with interpreting vector fields if you can get yourself into that mind state. Here are some examples, and my God, these took me a long time to draw. And so don't yell at me when I let you guys out early. But notice that the length of these vectors are getting longer as we move away from the origin. Which makes sense, right? As the values of x and y increase, you would be expecting that these vectors are getting longer. So just keep in mind that the length of the vector or the magnitude of the vector is really telling you how strongly a force is pushing you. Right? So if I were to drop you in here, you'd be getting hammered by wind. If I put you in the middle here, this would be like the eye of the storm. You'd feel nothing. Here's another one. Fx is equal to y sine x. So at every point xy here, you want to draw the vector y sine x. So you can get really interesting behaviors. You'll hear the word particle a lot. I won't use it, but the physics people, maybe even the fluids people, I don't know if that's biology or not, but they'll talk about throwing a particulate matter into this vector field. So if you were to, and next week we're going to talk a little bit about this more. So if I sort of imagine this is water, and I put a rubber ducky here. Right? The rubber ducky is going to move along this path. Right? When I put the rubber ducky here, it's going to get tossed into this eddy. Right? So we want to be able to study mathematically, if I put you here and I check in on you 6 minutes later, where can I expect to find you? Right? This is another fun one. This tells you if I drop you here, you're going to come in and you're going to move around this thing here. Right? If anyone's interested in developing for video games and stuff, this is the vector fields would be what would describe smoke or water moving. Right? This is the serious mathematics that they need to do that type of stuff. So this was ln 1 plus y squared, ln 1 plus x squared. So you guys comfortable with this? Good, because quiz. We're now going to do, I've ripped these out of the Stewart Calculus book. Right? So these, and I've given you a lot. So this week's WebAssign is going to be longer than usual. Because you're not going to have, it's all multiple choice basically. But there's a lot of it. Right? Because there won't be much working, but you're going to have to do maybe 10 questions. Yes? As in the WebAssign? I don't understand, but I can say assuredly that if I teach it in class, you should know it, that it's testable. So you want the quizzes to be closer to what you learn in lecture? Like, you're telling me that they're temporarily off, right? That you're getting tested on week 4 material, even though it's week 7. Are you being quizzed on material that I have yet to present to you? Because that would be a problem. Well, your final for sure will be comprehensive. So there's no escaping that. To answer your first question, I don't have much input on the quizzes, not because I'm not allowed to. It's because I'm not the course coordinator and it's not my job. If you want me to talk to Bjorn about this, I can. So what I'm hearing from you is you just want a better indication of what's going to be on the quiz so you can study better. Okay, I'll talk to Bjorn about that. But just ask Bjorn in class, right? He's very receptive. He very much wants to have good reviews this year. So we've been getting pretty horrible reviews from this class in particular. So we're doing our damnedest to do better. Well, what I told him is we'll just fail all of you if we get bad reviews, right? It's a simple solution. Okay, no, but that is a good point. Ask him, but I will also ask him about it. But I don't set the quizzes, right? So don't hold it against me. I just show up when they ask me to. Okay, anyways, so all of your homework this week is going to be questions exactly like this. This is from the Stewart directly. So let's do it now together. Because if we can do it now together, you should be able to do it when you go home. I think this week is less randomized than most, so you can work in partners or something if you want, because the questions will be the same. You have 100 chances this time around. You have 100 tries to get a multiple choice question of 4 things correct. Okay, with the caveat that they're being given to you in a randomized order, hopefully. Right? You should be getting all your web assigned questions correct. Right? They're gimme marks. The reason that there's so many this week is because practice really is the only way to learn, and I can assure you that there's going to be some of these questions on your exam. Right? Let's focus on getting all the easy marks in the exam so you can use the rest of your time to do the hard ones. Okay, but back to this question. 3. Why? What's minus 2? Why is minus 2? Okay, so these are the strategies that we need to start coming up with, right? Because there's real no solution here. We have to ask ourselves, well, why can't it be this one, right? So what you said is a good observation. If we look at y equals minus 2 down here, right? The vector field, well, the second component here is always going to be 0, and the first component is always going to be minus 2. Is it the case that at y equals minus 2, we have a bunch of arrows pointing left? Left? Sorry, it's all backwards down here in Australia, right? Yes. Okay. But that's not enough. We need to determine that none of the other options also would satisfy that condition, right? That is, it is sufficient that this is well, it is true that we can't rule out 3 yet, right? But we can rule out 1, 2, and 4 probably. Okay, but let's make ourselves feel better about this. What else can we check on this to make ourselves feel better? Yeah, pretty much. Well, let's look up in this region. We see that as we move up, we're being pushed more to the right. Right? Is that what this vector is saying? Well, if you're going up, yeah, you will be being pushed to the right harder, right? Because these vectors are getting larger as we move up. That's the other thing that we can observe. Right, that's another good observation. At y equals 0, you'd have the vector 0, 2. Right, so at y equals 0, we should have all up-facing arrows. Right, so everyone get out your clicker. Who thinks it's 1? Who thinks it's 2? Who thinks it's 3? Click. 4? None of the above? Good on you, mate. The answer is 3. 3. That was the answer. Here's another one. And we can rule out 3, because we've already used it. What? Well, you tell me. Which one is it? And then tell me your reasoning. Well, what I see here is that if on the x equals y line, you're sort of always moving in that direction. 2. Okay, so if we think it's 2, then at y equals 0, we should always be pointing towards x up. So that means the farther along x we move, we should have higher and higher arrows on the x-axis. Is that the case? I don't think so. Any ideas of what we should do? Well, what's happening here at 0? The cos of 0 is what? 1? So do we have the vector 1, 0 at the origin? Doesn't look like it. If I can rule out 4, we can rule out 3. I ruled out 4. We've already had 3. We've ruled out 2. So this is probably none of the above. Oh, it's 2. Why is it 2? Who said 2? I'm sorry. You should come up here and lecture. What did I say that was wrong? Yeah, I said that at y equals 0, we should see at y equals 0, at every x, we should be pointing up. But not in the negative side of, okay, yeah. Well, at y, I said something, but then I didn't check it properly. So here's the 0 line, x equals 0. And I forgot. If we move left, it's negative x. So we're not going to have upward-facing arrows. We're going to have downward-facing arrows, right? And as we move further and further along from the origin here, they're getting longer. And the same is true as we move to the right. Okay, so we've checked off 3, we've checked off 2. Oh, it's sort of an artifact of the drawing. There should be really nothing there. It's a vector of 0 magnitude, so it just drew the head. But we'll ignore it. I'm just saying ignore it. It shouldn't be there. Because it just drew the head of a vector that doesn't exist. Give me a break. I drew all the other arrows properly. All right, what about this one? So what have we done? We've done 2, we've done 4. Oh, sorry, we've done 2 and we've done 3. So this is either 1 or 4. So, any guesses? Well, if we look at this x equals 0, right? If we just change, if here is x equals 0, and as we're moving up, it seems that we're always pointing to the left. Except if we get really close to 0. Okay, so it can't be 1. If this was 1, I would be able to tell exactly what's happening on the x equals 0 axis. Right? You should have longer and longer arrows pointing up, pointing down and pointing up. So I can only conclude that this is 4. But who agrees with me? Shouldn't be overly confident. Hooray! So what's this one? 1, right? But let's investigate it a little bit. So what is this saying? This is saying at every point x, y that we should draw a vector in the x direction but reverse the y direction. So why is it impossible to move through here? Why is it sending us along the x-axis? Yeah, why do we have asymptotes? Well, as soon as you hit this line here, this y equals 0, the only thing they were able to do is move left. You can't move down. So you're never going to pass that threshold. Right? You can never pass this threshold from here to here, from here to here, from here to here, from here to here. Because as soon as you hit that line, you're traveling flat. you're still complaining about the 0, 0 vector. Technically, a 0, 0 vector is pointing in every direction, if you'd like. So that middle one is not wrong. Okay, so we did 2D ones. Now let's do 3D ones. Right? And again, this is basically what your homework's going to be. And I'm just trying to waffle, because I really don't want to let you out an hour early, but I doubt you guys will care. But we're just going to do the same thing we did with the 2D ones for 3D. Right, so a three-dimensional vector field is given by a vector function, which takes something and gives you a vector back in 3 dimensions. Right, so in the same way that we were drawing vectors in 2D, I can draw 3D vectors like this. You go to the point in 3D, and then you draw a vector from that point in R3. Okay? For you physicists, these 3D fields are very useful, right, because the world, the universe that we're modeling is in R3. In particular, here's the equation for the gravitational force field of a point mass of mass m. What are big M and big G? Yes, which ones? The M and G constant. He's not wrong, everyone. I'm going to guess that G's for gravity, but what's M for? Mass of what? Mass of Earth? I don't actually know the answer. I had to look it up. And I've already forgotten. I know that G's for gravity. Well, let's look it up. Is anyone in here studying physics or engineering? You should all be ashamed of yourselves. Good. What should I look up? Physical constants. G is the gravitational constant. Did it say Planck mass? Here, Planck mass. Whatever that means. I know what a Planck length is. The unit of mass, the mass of a flea egg. I don't know why this is important. We'll have to ask the physicists. Anyways, but here's a gravitational field, right? And it's given by this vector. Here's another more boring one, right? Where at each point in space, I'm saying just draw a vector which is representing the z component, right? So as you move higher, you're going to have longer arrows. As you move lower, you're going to have shorter ones until you pass into the negative threshold, in which case they get longer in the negative direction. Here's something that you wouldn't want to get trapped in, I reckon. You just sort of swirl around as you get stuck in the middle. We would never expect you to draw something like this. It'd be pointless, right? This is what computers are designed to do. I think you're going to be given a MATLAB assignment for drawing these vector fields. It is useful when you can start turning and looking at these things. Here's another one, y minus 2x, right? This is sort of moving you. Like you could, again, you just have to see this as flow, as some sort of liquid, and how this liquid is. And you threw a bunch of particles into the liquid to see how it's moving. Here's another one with an eddy down here. That's like sort of sending you up. Okay, but this is really the interesting stuff. How can we solve questions like this? As in the ones that will be appearing on your midterms exams and WebAssembly. Which function corresponds to the drawn vector field? One. Why? Right. It's the only function. So if you look at here, you're seeing a bunch of exactly the same arrows. This is the only selection among all 4 of them whose vector is not changing somehow as you move around. So that was a good police work, I guess. Wasn't there a police show with a mathematician on it? It was called Numbers or something like that. Yeah. That's what I'm going to go into after this. Forensic mathematics. What about this one? seems to be a vector function which is repulsed by the origin. So you move to a position, and that vector says, keep moving in the same direction you walked here, but fast. Okay? So I think it's 3 as well. Oh. Damn it. Okay, well, here's a vector field which is moving you from left to right, always left to right. Well, okay, left to right about how I drew it. I should say this better. Regardless where you are in Z, you are going to be pushed in the direction 1, 2, right, in the xy plane, right? So if you took this and you cut it, you would see the same thing at every level, and the only function that represents that is none of the above, correct? None of the above. 4. So this last one is what? Okay. But let's see that 2 is what we would expect. Because we look at this and we see arrows, all the arrows are pointing up, anywhere we are. Right? That's the first piece of information that we should extract from this. And in fact, all these arrows look to be the same length, right? Is that even true? Yeah. You go to XY. No. They're not all going to be the same length. They are getting. They should be getting longer as you move away from the origin. But the point is, they're all pointing upward, even in the negative Z region. Right? So that's why we can associate 2 with this. Okay? So your homework is going to be this sort of investigatory work. Right? There's no certain way to determine these things. You just have to look at the thing and try and delete the functions which don't satisfy it. Right? But there's a lot of them, so you'll get a bunch of practice. Right? There won't be much legwork this week, but you will have to think. So I deeply apologize for that inconvenience. Okay, gradient fields. We don't really care about vector fields. We care about vector fields insofar that gradient fields are vector fields, right? But really, gradient fields is all that we care about. So recall the gradient function, right? You give me a function f, a surface, and I'm going to give you back a vector which gives me the partial derivatives in each direction as a vector. Right? So again, if you give me f of x and y, its gradient vector is partial f, partial x, partial f, partial y, and if it's a 3D one, you also do partial f, partial z. The point is if you have a scalar function f and you take its gradient, you've turned a scalar function into a vector function. And now that we have a vector function, we can draw vector fields. But these are very special vector fields. So it's like this, right? So here's the simplest example I can give you. If you have some sort of plane that's moving up, the gradient field is telling you what is how can I put this? If we want to play a game, and this game is get to the highest position on this surface, the gradient vectors are the things that are telling you how to maybe get to the highest point on the surface, right? So it's another way of saying it is at any point on this surface, the gradient vector is telling you the direction of steepest descent. It's saying this is the hardest way to climb, and I'm guessing that the hardest way to climb is going to lead to the highest position on this surface. Okay? We don't normally draw these gradient fields like this. We usually lift the vectors off and just look at them like this. Right? You have to use your imaginations to 3D-ize them. Right? And we don't normally write, so it's colored to give you the elevation of the surface, but we don't even normally include the color. I'm just putting it in there to aid us in our understanding. Right? So from this gradient field, we can say, okay, if this means that I should head in this direction to the highest part, but it's getting steeper and steeper and steeper and steeper. Right? And you can see that from this picture, that you're getting steeper and steeper and steeper. So that was an easy one. So these are what these gradient functions are going to look like normally. And you note that these gradient vectors, by definition, are going to be tangent to these lines. Right? These are, you remember contour lines? Right, I've cut a surface a bunch of times. I've put those lines into here, and I've drawn these vectors like I did in the one before. Right? So the contour lines are the function x squared y minus y cubed. Its gradient is given by the, its gradient field is given by the vector gradient 2x. That's what happens when I take the derivative of this with respect, no, that is wrong. This should be 2xy, shouldn't it? There should be a y here. Which is fine, because this is drawn correctly, I just didn't. So the partial derivative of x squared y minus y cubed is 2xy. The partial derivative of this with respect to y is x squared minus 3y squared. So what is this telling us? This is telling us these lighter lines indicate that you're lower. So this is sort of saying, well, you're getting out of a hole. And here, since the lines are getting darker, this is sort of saying, well, you're moving upwards. All right, so you, in your mind, need to take a picture like this and realize that it's a picture that's been drawn on a surface like this. Right? This is easy to draw. This is harder to draw. This really requires a computer to draw. But that's what they're telling us. Right? Again, the vectors are pointing you in the position which it feels is the direction to head if you want to get to the highest points on the surface, which is useful when you want to optimize something. Right? So this is saying, oh, we're pretty steep here, so you gotta head up. Right? And then, all right, maybe go this way. And, right? Even here, it's telling you to turn around and move up here. Right? Because as you know, who knows if you're at the highest position on a surface or not. You may have increasingly higher cliffs. Right? This is the point of the other part of this class. You're learning all these numerical methods, like Newton's method and Euler's method, in order to find the global or minimums of these. Right? That's why me and Bjorn are sort of working hand in hand here. And so again, the vector field for this is what happens when we pull all these vectors off of it and put them on a plane. Okay, what can you tell me about this surface? So speaking of mountains and sinkholes and valleys, what do we have here on the left? It's mainly flat? How can something that's mainly flat have these contours? Well, well, this is it. So I wouldn't characterize this as mainly flat. Oh, so it's flat outside of the region that I'm illustrating. Got it. It is true that this is mainly flat at the part that I'm not. Well, who knows? Who knows what happens there? I just simply stopped drawing. Right? You'd have to get more of this picture. Plus, if I zoom far enough away from this, it appears flat. What do you mean by flat? If I look at anything close enough, it becomes flat. If I go far enough away, it looks flat. You'll learn about curvature elsewhere. The point is that one of these things are depressed, one of these things is high. Right? So what are the arrows doing? Well, it's saying, get out of this sinkhole. This is not the highest part of this mountain. Get out. But it doesn't know which way to exit. It just knows that you're at the bottom of the hole. You need to not be at the bottom of the hole to find the highest part. Right? So, and if you had a numerical method for trying to find this, going this way would be a crappy start. Right? You need to find ways to correct that. But if you go to the top here, what happens? This is interesting. This is how you sort of know that you found a local maximum. That all the arrows are pointing towards you. Right? You are the steepest descent in every direction. Right? So that's why all these arrows look so crowded up here. Because everyone is pointing, yes, that is the peak. Right? So the arrows, the length of the arrows really is an indication of how hard you'll have to climb. Right? If you're at one of these points. Right? So again, we don't draw this. Well, we have this, which really indicates this, which is drawn like this. Right? So this is the state of mind that you have to get yourself into when dealing with these questions. Okay. Match the plot with the gradient field. Huh? Who said 3? It's cheating. Hey, if you're going to cheat, at least cheat in such a way that you're getting the correct answers. First step of cheating. I always tell my students, if you're going to cheat off someone else, make sure that person is smarter than you. Right? Well, then you'll fail. I don't know how to do any of this. Okay, so what's the first thing that we need to do in questions like this where we're talking about gradient fields? Well, are any of these functions a vector function? No. So none of these functions can match with this picture. But I'm not asking for a vector field, I'm asking for a gradient field. So the first thing that we need to do is look at the blank of these functions. No. Well, maybe. The answer is gradient. Gradient. Gradients is the answer. We need to look at the gradients of each of these functions to turn them into vectors. What is the gradient of the first function here? I'll break it down to you. It's a vector of two components. Its first component is going to be x squared plus y squared. Take the derivative with respect to x. 2x. What's the derivative with respect to y? 2y. What's the gradient? Perfect. So the gradient of the first one is 2x, 2y. The second one is going to be, I should have wrote this somewhere. Maybe I can do this. Although, if you're watching at home on the Echo, well, you should have come to class, I guess. Let me see. Send to left projector. No, I want the right one. The orientation on here is for me, so that's the right projector. I don't like that. Okay, so let's write down all the gradients for these things, so I can have them on hand. Okay, so the gradient for one was what? You said 2x, 2y. What's the gradient of 2? What? This. Well, if you want to multiply by the derivative of the inside, you get 1. So I can put that there. Makes you feel better. What? We're going to have the same thing here, right? 3 is what? Just expand it, right? It's x squared plus x1. X squared plus y. And then the next one is what? X. Or? Don't do work until you absolutely have to, right? Because we know we're going to be able to isolate one of them by virtue of finding the solutions to the rest of them. Right? So work smarter, not harder. Or work like a mathematician and be lazy. Okay, so which one is this? Why? Which line? But okay, but this is a good strategy regardless of what you're working at. You want to look at things that are 0. You can look at y equals 0, x equals 0, x equals y equals minus x, and see what we're expecting, right? So this diagonal line, yeah, that would be a good thing to look at, right? Because it seems as we move, as x and y get bigger, so too do the lines that are coming out of them. So which one of our ones could do that? Yeah, it could be 2. It could also be 1. Okay, the other line. Which one? This one? Yeah, y equals minus x. What's happening here? If y equals minus x, yeah, then nothing's happening. Then we're collapsing. So, props to the educator. I'm so glad that was correct. Otherwise, I would look like an ass. Okay. What about this one? Something's being repulsed from the origin. Not 2. Right, so you go to any point, and it seems that it wants you to continue going in that direction, but maybe twice as hard. The 1 looks like a good candidate for this. All right. Yeah, this is the one that I'd want to say is the complicated one. Right? Well, because it looks complicated. Like, you would think that something that has this type of sophistication is going to need a more sophisticated equation than just linear stuff happening. Well, processes of elimination is a totally fine method of determining the solution to something. When x equals 0, there's no y component. Yeah, from the plot here, right? Well, the problem is we're not matching the equation to the plot. We're matching the plot to the gradient of the equation. We haven't written the gradient of 4 yet. I'm saying 4, but I don't really have a better reason than the ones I've described.
Another reason is
Mm-hmm. We don't have the gradient, though. How did you... Oh, for 3. Oh, yeah. So you're eliminating the only remaining option from it. Yeah, that's a better evidence than I have. I don't know. Go home and actually work out this. Like, if I was going to do this, I would do it very close to the origin, right? Because then you can just forget that the sign even is there. If you do it on very small values, you can treat everything linear. Okay. So we know this is 3. But let's at least assure ourselves that that should be the case. So for 3, we had the gradient 2x plus y x. So that means, okay, in the very least, this means as you move higher and higher in x, your arrow should be getting longer and longer and longer upwards. Yes. And it should be doing the same thing in the opposite direction as we move in the other direction. Yes. So you think you guys can be able to handle these questions for this week? There's a lot of them. Go ahead and work together. Go ahead and guess wrong. You have 100 tries to get, yeah. Yeah, well, it is possible to do it wrong. Right? You can guess incorrectly 100 times. Right? But I think it's 100 every question for the multiple choice ones. Like last year when I was teaching another class, we had these WebAssigns, and you had an unlimited number of attempts at them. So we were just interested that we just want you guys to practice. I don't really care about giving you guys marks. But anyways, look, I'll see you next week for line integrals. Sorry for cutting it short this week, but go home to your friends and lovers. Or go home to Netflix and a pillow. Then, sir, I cannot help you. If you don't have Netflix, I'm not surprised you don't have friends.